today's vlog, I'd like to talk a little bit about our typical R&D cycle here at Verus. We get bombarded by customers asking us to develop products for their car, and sometimes we don't feel that they fully understand how much work it takes for us to develop just one product. So I wanted to take you through our typical cycle of R&D and all the way to production. I have in front of me a wide range of some of the components we've designed over the years, from sheet metal to weldments, billet, casting, forging, and some of our carbon composite products. We are well versed in quite a bit. I will do my best to discuss with you the design process for each and how much work it takes to get to a finished product. So generally speaking, we start with a scan of the vehicle or a component of the vehicle. We use a handy handheld scanner, which then is connected to a laptop with software that basically takes a bunch of images of the object in the field and then creates a point cloud. Within the scanning software, we then take each individual scan and fuse it together. This creates a single object within the scanning software, which we can then export and use within CAD. Typically with a aerodynamic component, I will then design a rough design of what we believe we should build for the car. We generally do this to get a good starting point within CFD. I then hand off that solid part to Paul. Before we can even CFD a product, we actually have to create a CFD model of the vehicle, which is quite extensive as far as we have to take that scan data and then solidify it into a solid body. It is a very time-intensive process. So first we have to get that, and then we have to run a baseline of the factory car. Then we take the product that we designed and import it into CFD and compare the differences with the factory body and the now modified body with our components on it. After testing the components in CFD, we then optimize the components. Every product is optimized within Verus differently. Some components we cannot use the adjoint solver with yet. It just cannot perform the optimization function. Other components, like say our wing end plate, we were able to optimize within CFD as it is a simple model, and within ANSYS it can basically morph the model to improve performance, which is basically why you see some of the features in this. We then take that improved model of our CFD component and we bring it back into CAD so that we can design a manufacturable component from that. We have to take into consideration hard parts on the vehicle, and we have to ensure that it can actually be manufactured to hit a specific price point as well. Certain products at this point are then test printed. We have the CAD model, and instead of producing the part out of billet, carbon, forged steel, we actually print the product in plastic. It's less expensive and it actually reduces our time involvement in the design process. So it's actually really beneficial. We also test print like castings as well. So that would be the point, right now would be the point that we actually test print and test fit products in plastic. After we ensure that the test print, it actually fits the vehicle or the application, we can then actually produce a first article. Even though we have test prints at times, say like castings or forgings, the manufacturers want to ensure that the molds that they create are accurate and will produce a part that is perfect for us. So we have to do a test print, and sometimes, say castings or forgings, that's a 2 to 3 month process. Something like carbon, 2 month, billet, sometimes a month. Generally, we can just go to production with billet, as it's a process that doesn't deviate very much. Carbon and casting, sometimes we cannot go straight to production, but sometimes we do. So at this point, we test fit our first articles on car or in the application that it's used in, say like a header collector. After we test fit that first article, we make any tweaks or changes to the models that are necessary. Say this clutch fork, initially it was a little thick right here from the forge process. There was a little bit of flash where the two mold dies came together. We actually had to modify the mold off the first article to ensure that it does not bind on the throw bearing. Something like this casting, we had to move a bung, stuff like that. Doesn't always happen, and we hope it doesn't happen, especially with 3D test printed part, but sometimes the manufacturing process deviates from what our design intent requires. So once we make those revisions, if there are any, fingers crossed there aren't, we can then go to production. Just because a product is in production from us does not mean that our revision process does not happen. Sometimes we get feedback from customers that warrant a revision, and we have changed the FRS BRZ rear diffuser at least a dozen times as we have improved our performance and strength and rigidity through learning other products. So I went through a quick R&D cycle of a CFD component, a product that then sees, say, a structural strain like the lower control arm or the clutch forks. We will do the same process and go into FEA, which is finite element analysis, and that checks the strain and stress of the product. We then go back and forth between CAD and FEA to improve the performance of the product, take out weight where we can, which is why we have one of the lightest weight lower control arms on the market. And then it's always a balance between creating a lighter component and increasing machine time, or creating a lighter component and decreasing stress. This also happens with our CFD products. The GT4 front splitter, we've probably revised it 7 times before even producing it, just to get our cost down and so that it fits as designed. We initially designed a front splitter that we thought we could fit on the car and it would function to create the aero balance that we needed for the GT4. But then as we went to design the actual manufactured product, we realized we couldn't actually manufacture a product that would net the same performance that the analysis created. So then we had to go back to analysis, create another model off of our closer manufactured model, go back to analysis, ensure that it actually worked, go back to manufacturing, figure out how to make that a manufactured part. We then saw, wow, this has a lot of components. We should probably actually create a more simple model, but somehow ensure that the same downforce was created. So then we went back to CFD, created another model, et cetera, et cetera. It was a very iterative process, and it's taken us many months. Most times products aren't that design intensive, but sometimes they are, and it's a fight. It's fun to us, but we're engineers. So I've gone over a rough overview of how our R&D process goes. I can discuss how long it takes to go from a first idea to a finished product. Our rear diffusers are generally between 3 and 4 months from first design to a production piece. Simple sheet metal parts like this can be done in about a month. Billet parts 1 to 2 months. Casting and forging 6 to 9 months, and then some more complex carbon work. Specifically these front air dams that we've been working on. Those can take 6 to 9 to 12 months long from what we have seen so far. I'd like to stress that this is a real basic overview of how we do R&D at Verus ourselves. Obviously we also have some testing, but this was just from design to production, testing not included. And now you can kind of see possibly why it takes us quite a bit of time and effort and money to produce a product, and why we can't just go out and produce just about anything. We have to do it with the laser focus and with the hope that we'll actually a return on our investment, because our investment is very time and monetarily intensive. Yeah, I think that's about it for this blog post. If you guys like what you heard, or want to know more about, like, say, manufacturing processes, I'd love to do some more. Leave a comment on YouTube, Facebook, Instagram, or whatever you see this. I'm pretty sure it's Paul's turn next. So I'll sign out. Till next time.